Hi again. Today we are going to explore the fundamental building block of matter, atoms. But here's a question to get you thinking. If you could shrink down to the size of an atom, what would you actually see? Would it look like a tiny solar system with planets orbiting the sun? By the end of today's lecture, you'll understand the true structure of atoms and how we identify different elements using two crucial numbers that act like an atom fingerprint. Let's start with a journey through time. The ancient Greeks coined the term atomos, meaning indivisible, because they believed atoms were the smallest possible pieces of matter, like Legos blocks that couldn't be broken down further. This idea remained unchanged for over 2,000 years until John Dalton in 1803 proposed that elements were composed of identical indivisible atoms. But then came the breakthrough discovery that changed everything. In 1897, J. Thomson discovered the electron, proving atoms weren't indivisible after all. Then in 1909, Ernest Rutherford conducted his famous gold foil experiment and discovered something shocking. Atoms are mostly empty space with a dense center called the nucleus. Here's a mind-blowing size comparison. If the nucleus were the size of a marble sitting at the center of the football stadium, the electrons would be buzzing around somewhere in the stands. The atom is 99.9% empty space. Today we know that the nucleus contains protons and neutrons, while electrons form a cloud around the nucleus. This structure is the foundation for understanding atomic number and mass. Now let's explore how we identify different elements. Every element has a unique identifier called the atomic number, represented by the letter Z. The atomic number equals the number of protons in the nucleus. And here's the key point. The number of protons determines what element you have. Think of it this way. Atomic number is like a person's fingerprint. It's unique and unchangeable. Hydrogen always has one proton, so Z equals 1. Carbon always has 6 protons, so Z equals 6. Gold always has 79 protons, so Z for gold equals 79. Change the number of protons and you have changed the element entirely. Here's an important rule for neutral atoms. The number of protons always equals the numbers of electrons. So if carbon has 6 protons, it also has 6 electrons in its neutral state. The periodic table is organized by increasing atomic number, not by mass, as Mendeleev originally proposed. This organization reveals the periodic patterns we see in element properties. But atomic number only tells us about protons. To understand an atom mass, we need another number. While atomic number identifies the element, mass number tells us about the atom total nuclear mass. Mass number, represented by the letter A, equals the number of protons plus the number of neutrons. The mathematical relationship is simple. A equals Z plus N, where N is the number of neutrons. Let's look at carbon 12 as an example. The 12 is the mass number, telling us this carbon atom has 12 particles in its nucleus. Since carbon has 6 protons, it must have 6 neutrons. 6 protons plus 6 neutrons equals 12. Why don't we count electrons in mass number? Because electrons are incredibly light. about 1 over 1836 the mass of a proton. It's like trying to weigh a car while including the weight of a few paper clips inside it. We can write atomic notation in several ways. Carbon 12 can be written as C, and we put the 12 above the letter C, or C-12, or simply carbon 12, as we already written it. The key is understanding that the mass number always represents the total number of nuclear particles. When solving atomic structure problems, follow this three-step strategy. First, identify what you are given. Second, use the relationship A equals Z plus N. Third, solve for the missing quantity. Let's work through an example. Find the number of neutrons in phosphorus 31. Step 1. From the periodic table, phosphorus has atomic number 15. So Z equals 15. The mass number A equals 31. Step 2. Using A equals Z plus N, we get 31 equals 15 plus N. Step 3. Solving for N gives us 16 neutrons. Now here is another example. What's the mass number of sulfur with 18 neutrons? From the periodic table, sulfur has atomic number 16. We are told N equals 18. Using A equals Z plus N, we get A equals 16 plus 18, which equals 34. So this is sulfur 34. The key is remembering that for neutral atoms, the number of electrons always equals the number of protons, which equals the atomic number. Now let's explore how we measure atomic mass. Scientists needed a convenient way to express atomic masses, so they created the atomic mass unit, or AMU. One AMU is defined as exactly 1 over 12 the mass of a carbon 12 atom. Here are the approximate masses. Protons weigh about 1.007 AMU, neutrons about 1.009 AMU, and electron only 0.0005 AMU. Notice that protons and neutrons have nearly identical masses. But here where it gets interesting. If you look at the periodic table, chlorine's atomic mass is 35.44 AMU. How can this be if atomic masses should be whole numbers? The answer is isotopes, atoms of the same element with different numbers of neutrons. Chlorine has two main isotopes. Chlorine 35 at 34.97 AMU with 75.77% abundance, and chlorine 37 at 36.97 AMU with 24.23% abundance. The periodic table shows us the weighted average of these isotopes. To calculate average atomic mass, we multiply each isotope's mass by its decimal abundance and add them together, like 34.97 times 0.7577 plus 36.97 times 0.2423, which will equal 35.45 AMU. This explains why atomic masses aren't whole numbers. They reflect the natural mixtures of isotopes found on Earth. So this is all for this lecture. See you in the next lecture.